So hello everyone, welcome back to the channel. In today's video, we are going to cover one of the most powerful supervised machine learning algorithm, that is support vector machine, or we can also call it as SVM. So let's start with first of all, why we not just use a line as we use in linear regression. So let's start it with a motivating example. Suppose we have two groups of point. Okay, one group represent the spam emails and the other represent the non-spam emails. Now imagine these points are being plotted on a graph using features like word count and the number of links in the email. Many different line can separate these two classes perfectly, but the question is that which line should be chosen. A normal classifier may choose any separating line, but SVM chooses the best possible line. Now how it makes it the best? It via maximizing the margin between them. Okay, so the next big question is that what is this margin? So margin means the distance between the separating boundary and the nearest data point from both of the classes. SVM tries to maximize this margin, and because a larger margin means a better generalization, less sensitivity to noise, and a better performance on unseen data. Okay, so instead of just separating out the classes, SVM try to separate them with the max possible gap. Yeah, so let's move forward towards what is SVM. Let's go towards some of the information about SVM. So SVM stand for support vector machine. It is basically a supervised learning algorithm which is mainly used in classification and sometimes regression. SVM, what it do is it finds a hyperplane that separate the data into classes. In 2D, hyperplane is a line. In 3D, it become a plane, and in higher dimension, you can call this as a normal hyperplane. Now the equation for the hyperplane sometimes looks like the W transpose into X plus B equals to 0. Here W is the weight vector, X is the input features, and B is the bias. Now prediction is done using the sign of WT X plus B. If the output is positive, then the class becomes +1, and if negative, then the class become -1. Now moving forward, we have a topic support vector. Okay, so now comes the most conceptual part of it. Support vector are the data points closest to the decision boundary. These points are extremely important because they define the position of the hyperplane. If support vector moves, the boundary changes. Other points don't really matter much. Okay, now we have two types of margin. One is the hard margin, another one is the soft margin. So starting with the hard margin, SVM. So what it does is that the data is perfectly linearly separable, means there is no overlapping, no noise, every point can be classified correctly. The optimization is being done by minimizing half mod of W square subjected to yi in bracket W transpose xi plus b is always greater than or equal to 1. Okay, this may look sometimes scary, but the intuition is very simple. SVM uses to minimize the magnitude of W, and minimize W actually means maximizing the margin. The margin width become 2 upon mod of W. So smaller W means larger margin. Moving forward, we have a dual formula. To solve SVM efficiently, we convert the optimization problem into another form called as the dual formulation. Here we uses the Lagrange's multipliers called as the alpha values. One of the important point is that only support vector have a non-zero alpha value. That means only support vector contributes to the final boundary. Yeah. So moving forward towards the second part, that is the soft margin. In real life, data is noisy. Perfect separation is very rare and impossible. So hard margin SVM is usually impractical. That's why we use the soft margin. We have a point here that is called as the slack variable. Soft margin SVM introduce slack variable called as xi. These variable allow some points inside the margin or even misclassification point. Optimization become min of half mod w square plus c summation of all from I equals to 1 to n. This sign is called as the slack variable. Okay, so this slack variable for the I values. Okay, here c is very important hyperparameter. It's basically a hyperparameter that controls the margin size and the classification error. If c is large, then SVM tries to avoid the mistake, margin becomes smaller, model may overfit. But if C is smaller, then more mistakes are being allowed, margin become wider, and model become more generalized. Okay, so large C means low bias high variance, and small c means high bias low variance. Yep. Moving forward towards the hinge loss. Soft margin SVM can also understood using the hinge loss. The hinge loss formula is max of 0 comma 1 minus yi wt xi plus b. What does now the whole point is about the intuition. So if a point is correctly classified and outside the margin, the loss becomes 0. If it lies inside the margin or is misclassified, then the loss become positive. So hinge loss penalize the bad classification. Moving forward, we have a kernel trick. Now, coming on one of the coolest topic in the machine learning, this kernel trick. Sometimes data is not linearly separable. For example, imagining a circular data pattern, so straight line cannot help. So what kernel do is that kernels transform data into a higher dimension, which separate them easily. And the best part is SVM does not explicitly compute the high dimensional mapping. So this is called as the kernel trick. Now some of the most common kernels are the linear kernel, which we use to separate the linear data. Then we have the polynomial kernel. We have the RBF or the Gaussian kernel. Mostly used for kernel is this, which is being written in the exponential form. Moving forward, we can see some of the limitation of SVM. So first of all, SVM become very slow for the large data set due to the training complexity. Second, choosing the correct kernel is difficult. Wrong kernel can give you a very bad performance. Third one is SVM is naturally binary classification, is naturally for the binary classification only. Okay. Fourth one is that you does not get the output probability directly as we are getting in the decision tree and the random forest part. And finally, that the feature scaling is extremely important. Like unlike the previous algorithms where feature scaling and engineering is not so important, but SVM required a feature scaling before being processed. Okay, so now moving forward is a quick summary. So what we have done is we have covered SVM from the basic to a medium level and got an intuition about this.